So in this video, we will discuss the equations of motion, which I call the Utsav equations. Now the reason why I call them the Utsav equations, celebration time, yes. No, I call them the Utsav equations because U is for initial velocity, T is for time, S is for displacement, A is for acceleration, and V is for velocity. So these are the standard symbols for these quantities. And the Utsav equations actually help us find out the relationship between these quantities and how these quantities add up together. So the Utsav equations are 4 in number. The first one is V equals to U plus AT. The second is S is equal to V plus U upon 2 multiplied by T. The third one is S is equal to V square minus U square upon 2A. And the fourth one is S is equal to UT plus half AT square. Now we can use these equations in order to determine the displacement, the velocity, the time, the acceleration, the initial velocity, whatever. However, do understand that all these equations are valid only when the acceleration is uniform. Now let us understand the derivation of these equations. This is not in your syllabus, but I'll still explain that to you. The first one is, for the first equation, V equals to U plus AT. Now we know that the acceleration A equals to the final velocity V minus the initial velocity U upon T. Note that V and U are instantaneous velocities. So we simplify this equation. This equation becomes AT equals to V plus U, and therefore we get the equation V equals to U plus AT. So that's the first equation. The second equation is S is equal to V plus U upon 2 multiplied by T. Now we know that the total displacement is equal to average velocity into time. Why? Because the average velocity is equal to total displacement upon total time. Now whenever a body is accelerating, if we want to find out the average velocity, then the average velocity will be the average of the initial and the final velocity. That is, if the body is moving with uniform acceleration, the average velocity would be equal to V plus U upon 2. And when we replace the value of average velocity in the equation above, we get the total displacement S is equal to V plus U upon 2 multiplied by T. The third equation, S is equal to V square minus U square upon 2A. So from the previous derivation, we know that S is equal to V plus U upon 2 multiplied by T. And therefore S would be equal to V plus U upon 2 multiplied by, we replace the value of T from the equation of acceleration. T equals to V minus U upon A. So therefore S becomes V square minus U square upon 2A. That's the third equation. And the fourth one is S is equal to UT plus half AT square. So same thing, we know that S is equal to V plus U upon 2 multiplied by T, and we replace the value of V in this equation. We know that V equals to U plus AT. So S is equal to U plus AT plus U upon 2 multiplied by T, and that becomes S is equal to UT plus half AT square. So these are the 4 equations and their derivations. Now let us look at some examples that we have solved using these equations. The first one is about a bike. A bike starts from rest and achieves a velocity of 54 km per hour in 10 seconds. Assuming that the bike is traveling along a straight road, how much distance does it travel in this time? Now here we know that the initial velocity is 0. The final velocity, which is equal to 54 km per hour, becomes 15 meters per second, and the time is 10 seconds. So what equation do we use? We have a very simple equation. S is equal to V plus U upon 2 multiplied by T. And when we replace the values, we get the distance as 75 meters. Next example. A bus traveling at 18 km per hour accelerates uniformly along a straight road at the rate of 1.5 meters per second square for 6 seconds. Determine the distance traveled by the bus in these 6 seconds. Here, the initial velocity is equal to 10 meters per second. The acceleration is equal to 1.5 meters per second square, and the time is 6 seconds. And we use the equation S is equal to ut plus half at square because we only know u, a and t, and when we replace the values we get the distance as 87 meters. Example number 3. A train starting from rest moves along a straight track and attains a velocity of 20 meters per second in 200 seconds. Assuming that the acceleration is uniform, find the distance traveled by the train for attaining this velocity. So here the initial velocity is 0, the final velocity is 20 meters per second, and the time is 200 seconds. Now we do not know the acceleration over here, so we need to find the acceleration. So the acceleration would be given by the formula v minus u upon t, and when we replace the values we get the acceleration as 0.1 meters per second square, a very small amount. And then we used another equation to find out the distance, and we use the formula v square minus u square upon 2a, and when we replace the values we get s is equal to 2000 meters. So the distance is 2 kilometers. Last example. A car starts from rest upon a straight road and attains a velocity of 25 meters per second in 10 seconds. After this, the car moves with uniform velocity. Find the distance traveled by the car in 30 seconds since it started its journey. Now here the journey is in 2 parts. So we need to find out the distance traveled in each of these parts separately and then add them. So we first find the acceleration, which is equal to 2.5 meters per second square. To find out the distance traveled in the first 10 seconds, this is accelerated motion, so we need to use the formula s is equal to v square minus u square upon 2a, and we get s as 125 meters. Now after this the car moves with uniform velocity. For how long? 30 minus 10, 20 seconds. So the distance traveled in these 20 seconds would be simply given by the formula velocity into time, because that is uniform velocity, and that is equal to 500 meters. When we add both of these, we get the total distance traveled in 30 seconds, which is equal to 625 meters. So that's all in this video and in this chapter. In the next video we will start with a new chapter on laws of motion, in which we will introduce ourselves to the concept of force.